All right, so here's another way to show that functions are linearly independent. Okay? This idea is called wronskians. And we call it wronskian because it was invented by some mathematician named Wronski. So Wronski invented this thing called wronskian. So here's how it works. If determinant of f, g, h, f prime, g prime, h prime, f double prime, g double prime, h double prime is not equal to 0, then f, g, h are linearly independent. And this left side, this one is called the wronskian of f, g, h. That's how people write. W for the wronskian, and they list the functions, sometimes with comma or semicolons. That's what wronskian. That's how you use the wronskian. For two functions, you just take this 2 by 2. If you have 4 functions, you have to do f, g, h, and another function I, and then you have to differentiate 3 times to get a square matrix. So you can take wronskian of however many functions you have. You just have to differentiate enough times so that you get a square matrix. You probably learned that determinants can be only applied to square matrices. If you don't have a square matrix, you can't take the determinant. Okay? So if you have 4 functions, you have to differentiate 3 times so you get a 4 by 4 matrix. If you have 5 functions, you have to differentiate 4 times to get a 5 by 5 matrix, and so on and so on. Okay? All right. So here's an example, and you're probably going to like this better than the one before. Suppose I want to show that each to the x and e to the negative x are linearly independent. Okay? We had to go and prove something really wrong, right? But with the wronskian, here's what you can do. You can just take the wronskian of e to the x and e to the negative x, and that implies, well, what is this? This is the determinant. I'm going to write determinant by using 2 bars. You list the 2 functions, e to the x and e to the negative x. And you differentiate. What do I write here? Negative to negative x. Right? So those are the derivatives. And now we have a 2 by 2, which means I can take the determinant. So that's all you have to differentiate. And now you do AD minus BC. AD is e to the x times negative e to the negative x minus e to the negative x times e to the x. And that's equal to negative 1, because e to the negative x is 1 over e to the x, right? It's the reciprocal of this other one. So if I multiply 2, you get negative 1. Same thing here. So you get negative 2, and that's not equal to 0. Therefore, we know that these 2 are linearly independent. Okay. It's much better than having to prove it line by line, right? Okay, here's another example. What if we are suspicious of whether cosine x and sine x are different? We take cosine x, sine x, differentiating cosine, you get negative sine, differentiating sine, you get cosine, right? What's that? Cosine squared minus sine squared with another minus sign, right? What's this? 1. So that's not equal to 0. So in both cases, it's linearly independent. I should have written the conclusion here. Let me write the conclusion here. Thus, cosine x and sine x are linearly independent. All right, you might be wondering how this is possible. I mean, how did Wronski come up with such a nice machinery to easily prove whether it's linearly dependent or not? Okay? So by the way, if this is equal to 0, then you know that they're linearly dependent. Okay? So for example, this calculation is too long, so I don't want to do it, but I have a good example. So if you have wronskian of sine x, cosine x, and e to the ix, then you will see that it's equal to 0. And therefore, these are linearly dependent. So what is this? This is sine x, cosine x, e to the ix. Just write them down. And because I have 3, I should also have 3 going down. So differentiate sine, you get cosine. Differentiate one more time, you get negative sine. Differentiate cosine, you get negative sine. Differentiate negative sine, you get negative cosine. E to the ix differentiates to I times e to the ix. And here, I is square root of negative 1. So if you differentiate I, you get, if you square I, you get negative 1. So if you differentiate one more time, it will be negative of e to the x, because you get I squared. Now, how do you do determinants of 3 by 3? You have to expand, right? Using, you have to do a column expansion or row expansion, right? Okay, so let's just do a row expansion. So first you take sine, multiply by the submatrix obtained by deleting this row and the column containing this element that I just chose, right? So what goes in here? I should make it bigger. Negative sine x, I e to the ix, negative cosine x, negative e to the ix. And then let's choose the next element, which is cosine. And by the way, don't forget the checkerboard of signs that you need to apply when you do the expansion. So you need the checkerboard of signs. So if I take this element, for the blue, it has a minus, right? So I put the minus, cosine x. And then deleting the row and the column containing cosine x, I get cosine x, I times e to the ix, negative sine x, negative e to the ix. And then plus, for the green, I need plus e to the ix, cosine x, negative sine x, negative sine x, negative cosine x. Alright, so let's compute one by one. This one is sine x times positive e to the ix sine x plus I e to the ix cosine x. And minus cosine x, negative e to the ix cosine x, plus I e to the ix sine x. And then we have, what is it? Plus e to the ix negative cosine squared of x minus sine squared of x. So here, if you look at the signs, this is cosine times sine with a minus sign, and it's cosine times sine with a positive sign. They both have I times e to the ix in front, so these two will cancel if you expand. Okay? And then the other ones, you have cosine with a positive, whereas this says minus, right? So if you expand, then these two, this one will cancel with this one. And then if you look at this one, it's negative sine squared times e to the ix, and this one is positive sine squared times e to the ix. So these two will cancel. So after canceling everything, you see that at the end of the day, you get 0. Meaning that these three functions are linearly dependent. Okay. But you would never have guessed that they are, right? See, you have sine x, cosine x, e to the ix. They look completely different, but indeed there's a relationship between them. Okay. What's the linear relationship between them? Does anyone know? How are they related? According to our wronskian calculations, it says that they are related. How are they related?
They all equal 0?
Huh?
They all equal 0?
No.
The coefficients.
No. I mean, don't you know any formula that relates this with this and that?
No.
No? Really?
The I is really growing it all.
Okay. That's how they are related.
I don't know about that.
What is this thing called, by the way? Euler's identity, right? Yeah.
Strings.
So Euler's identity.
So that's what you get when you do all that stuff out?
No, you're not getting the point. And all this is saying is that there should be C1, C2, C3. When you add them up, you get 0, with not all of them 0. So all this calculation shows us is that there's some C1 sine x, C2 cosine x, plus C3 e to the ix. You will get 0 for certain C1, C2, and C3 values, not all of them 0. And I was just pointing out that there is indeed such numbers, and we know them. You can have C1 as I, C2 as 1, and C3 as?
1.
No!
-1.
Negative 1, thank you. Yeah. C3, if C3 is negative 1, C2 is 1, and C1 is I, this indeed gives you 0 for all values of x, and that means these are linearly, what, dependent or independent?
Independent.
Dependent! All right. It means that there is a linear dependence among the functions, okay? That means that one of the functions can be represented as the other ones, which is bad for us when we are trying to find independent solutions to differential equations. So, for example, if going back to our previous example where we had y triple prime equal to negative y prime, if you thought, oh, I found one solution, another solution, and a third solution, oh, we found all of the solution, then you'll be dead wrong. Because what you thought was an independent solution to this differential equation was indeed representable by the other one. So you should never pick this one as the third one. Okay? And that's what the wronskian is telling us. If you compute the wronskian and it gives you 0, that means, oh, you should this is no good, you should find another one. Okay? I already know that wronskian of these two is non-zero, so I know that these are independent. So that's good. But this is no good because if I choose the three of them and compute the wronskian, it's equal to 0, so this is no good. Okay, I need to find something else. And that something, as I said, should be a constant. Because the constant does satisfy this differential equation. So that's where linear independence comes into play. Okay.